right, good morning. Thank you all for coming. This talk is going to be covering geospatial analysis with Rails. So we're going to be doing some interesting things with maps and with geodata. So if you like maps and you like geospatial stuff, this talk is a good place for you to be. If you hate maps, this talk will probably make you hate them more. Just fair warning, we'll be doing some very fast-paced things. It'll be very technical, so kind of buckle your seatbelts. Really quick bio before we get started. My name is Daniel Azuma. I'm from Seattle area. I'm not a GIS professional. I'm not a geographer. I'm not a cartographer. I'm a Ruby developer. I'm like many of you. I've been working with Rails since about the 1.0 release, 2006. And during that time, I've done a lot of work in location mapping. I'm the author of RGeo, Active Record PostGIS Adapter, several other tools that some of you may have used to do work with geodata in Ruby. I currently serve as the chief architect at Perk. We're a Seattle area startup that does mobile-based instant deals, not daily deals, but instant deals directly on your smartphone. And of course, the obligatory commercial announcement, we are hiring. I noticed that the bulletin board out there is basically full of everyone's hiring, so just thought we'd throw our hat in the ring there. So here's what we're going to cover in this hour. At Perk, our service is very hyper-local in nature. We have to curate and analyze a lot of location data. Now, as Rails developers, many of us have already done some projects integrating, say, with Google Maps. Maybe we displayed a few pushpins on it indicating points of interest. But when your service is very location-centric, you often have to go beyond this. There are a lot of additional elements that you may have to model and analyze. There are many layers to how location really impacts people's lives and how location is part of the way that people use your application. And so when you start really digging deep, you realize that it can actually start getting challenging. There are a lot of concepts that you have to understand: coordinate systems, projections, vector versus raster data, lots of statistics, computational geometry. There's a learning curve involved. Now, I could spend this talk and probably several more trying to cover all this material, but in the interest of time, we're going to try something a little bit ambitious. We're just going to set the learning curve aside, and we'll just dive directly into looking at some code for a couple of interesting projects. So here's our agenda here. First, we're going to go over the software installation process for setting up a Rails app with geospatial capabilities. Then we'll look at some code for a couple of projects. The first one is a tool to help us visualize location activity. I collected about 50,000 location data points directly out of Perk's activity logs for a particular time, and we can see where people are using our app. The second one is a service that will tell us, given our location, our latitude and longitude, what time zone we're in. And then finally, if we don't go too far over time, we'll take a few questions at the end. Now, our goal here is to give you a 1,000-foot overview of how to go about writing these spatial applications. The intent is to get a general understanding of how all the pieces fit together. Now, you probably won't get all the details. We're going to go really fast. Don't worry about that. At the end, I'm going to provide a link where you can find a lot more resources to explore further. The slides will all be there. I've got all links to all the software, a bunch of other resources for further reading. So without further ado, let's just get started. So first, we're going to set up a Rails app to use geospatial features. Now, when you do serious work in geodata from Ruby, there are a few pieces of software that you need to install first. libgeos and libproj are a couple of C libraries. They perform most of the low-level math involved with geoanalysis. You can probably get them from your package manager. PostGIS is a spatial database. Now, if you do anything interesting with geodata, especially if you have lots of it, then you'll generally need help from your database. Most relational databases and even NoSQL stores by themselves generally don't really have these capabilities or don't have very much of them. So generally what you need is a special purpose database for doing spatial data. In PostGIS, what it is a plugin for the PostgreSQL database. It is the best open source database for spatial data that's available. I recommend using it, even if it means you have to migrate over to Postgres. Now, I know a lot of us as Rails developers, we're on MySQL. MySQL does have some spatial capabilities, but they're not very good. They're pretty much inferior. They're going to have trouble, even with the examples that we're going to go over today. So use PostGIS. You also need a couple of Ruby gems, starting with RGeo. RGeo provides some spatial data types for Ruby. We'll see a little bit of that in this talk. There are several other gems that we'll also see a little bit later. So let's start off by creating a Rails app. Again, we're going to start off with Postgres for the database since we want to use the PostGIS plugin, and because Postgres is a better database anyway. We'll add 3 gems to our Rails app. The first one is a special active record adapter. It's actually a subclass of the stock Postgres active record adapter, and it's been modified to access the PostGIS features. The second gem here is a tool for reading geodata from shapefiles. Shapefiles are a standard file format for downloading geodata from external sources, and we'll see some of that later on. And then third, Squeal is an active record enhancement that I found really useful for writing spatial queries. It's written by Ernie Miller. Version 1.0 actually just got released yesterday, so go check that out. Next, we'll need to modify the database.yml to configure a few things for the PostGIS adapter. All the specifics here on how to do this configuration are in the README for the active record adapter, so you can go check that out. We'll have add a few requires to active application.rb, and that's it. Now we can create a development database. The tools, particularly the PostGIS active record adapter, will automatically add all the geospatial capabilities into your database. There are a bunch of SQL functions, data types, and so forth that need to be added to your database to enable this. So now we've got a Rails app set up to support geospatial analysis. Now let's do some projects. So for our first project, we're going to visualize some location point data. Now, these could be check-ins. They could be other types of activity from, say, a mobile app. For our example, I'll load our database with about 50,000 location points directly from Perks activity logs for a particular time period. Now, our goal is going to be to visualize this data, maybe to see where in Seattle most of our activity was taking place at that time. So we'll start off by generating a model to hold the activity data. Now, some of us have done Rails projects before that supported location, and oftentimes one common practice is to store that location in separate latitude and longitude columns in your database. You can do this. It's kind of like using a string to store timestamps in your database. It's something that you can do, but then the database can't help you doing things like searching for timestamps, sorting, and generally interpreting that data. And that's why most databases actually provide you with a timestamp data type so that you can search, index, and so forth on that data. And it works the same way with location data. PostGIS adds some spatial data types, such as the one we're using here, point, to your database. Now, point is more than just a struct that includes latitude and longitude. It's actually a full-on abstract data type that lets you do things like compute distances, search for things spatially, and so forth directly in your database. So, rule of thumb, use the geospatial data types that are provided by your database. They'll really help. Now, here's our migration. We're going to do a little bit of configuration here. First thing we're going to do is tell PostGIS which coordinate system it should use to represent data in the database. Coordinate system is generally identified by this standard ID number, SRID. Stands for Spatial Reference ID. For our project, we're going to use SRID 3785. This coordinate system is actually the native Google Maps coordinate system. It's a Mercator projection. It's not latitude and longitude. So we're going to use this coordinate system instead of lat and longs to store data in the database. I'll cover a little bit about why we're going to do that a little bit later on. But for now, just note that we're actually using a Mercator projection to store the coordinates. And so whenever we have to interact with the database, we need to make sure that we may need to convert numbers, say, from latitude and longitude into a Mercator projection before we store it. Next, we'll add a database index to our point column. Now, database indexes, they all pretty much perform the same function, speed up searches. This one is marked as spatial, and so it is a little bit more sophisticated. It's one that's designed to handle geometric objects in 2 dimensions rather than 1. So it's a little bit more sophisticated, but generally performs the same function as the spatial data or the databases indexes that you've used before. Next, we'll look at the model. Generally, the active record adapter for PostGIS requires that you do a little bit of ceremony. You have to tell it what coordinate system you're using for the database and, in general, how to handle that spatial data in Ruby. And you do that by creating an RGO factory and associating that factory with a column in the database. In this case, we're going to use a smart factory. It understands latitude and longitude as well as the Google Maps projection and knows how to transform data between the two. You can read more about this and other issues regarding coordinate systems and factories on the link that I will provide at the end. So now we can rake DB migrate, database and model are all set up. Now let's obtain the data that we want to analyze. So I exported a bunch of latitude and longitude points from perks logs into a text file. So we've got about 50,000 of these lines. In a text file, I wrote a quick little script to read in that file and create records in our database. Now, again, the important part to note here is that our input file was in latitudes and longitudes, but our database was set up to use the Google Maps projection, the Mercator projection. So we need to transform the data into that coordinate system before we load it into the database. Now, let's take a look at how to query the data. Suppose we want our application to visualize our activity data on a map, say Google Maps. So this means that, in general, what we want to do with a database is we want to query for all the activity that lives within the map rectangle, some rectangular window like this. So let's write a scope in our active record model to select all the records within a rectangular window. Now, a couple things to note here. First of all, remember that the data in the database is in the Google Maps Mercator projection. So our queries need to use that coordinate system. So if we take latitudes and longitudes as the arguments to our scope, we need to convert them to the projection before we use them in the query. Secondly, for the query itself, it's really straightforward. We want to search in a rectangle, so we create a rectangular bounding box and find points that overlap it. This API is part of our Geo right here. Postgres provides a really convenient operator, the double ampersand, to test for overlap. So we can use that SQL to implement our scope. Now, incidentally, this is actually one of the main reasons why we're using the Google Maps coordinate system for our database rather than storing lats and longs in our database. And that is because we want to query a rectangle. And let me explain that. So consider a rectangle in Google Maps here on the left side. Now, if we were to look at that same region on the globe on the right side in geographic latitude and longitude coordinates, notice that it's no longer a rectangle. It's this funny trapezoidal-ish shape with curved boundaries. So if your database uses those coordinates, latitudes and longitudes, and you want to query that shape, you're going to have to compute what that shape is, and then you have to approximate it with a polygon, and then your database has to deal with that polygon. So you can do that, but it gets a lot more complicated. For this application, since our queries are rectangles in Google Maps, it makes much more sense for us to keep our database in that same coordinate system. That way, our queries stay rectangular, and that's what keeps this code simple. So bottom line, if you can choose what coordinate system to use for your database, then you need to choose wisely. Latitude and longitude, sometimes they're the right coordinate system, sometimes they're not. There might be a better alternative based on how you're going to query and use that data. Now, if you don't like writing SQL strings, Ernie Miller's Squeal Gem is really handy for constructing spatial queries. Basically, it lets you write SQL in Ruby using a DSL rather than interpolating strings. So for this query, it doesn't actually give us that much benefit yet, but when we get to more complex spatial queries, Squeal is going to really shine, and we'll see some of that a little bit later. So now we'll wrap this up in the quick controller. We'll render out these points that we've looked up in this query as pushpins on the Google map. And now we have an awesome visualization that makes it crystal clear what's going on in our app. Okay, well, maybe not. Well, we did have 50,000 data points here. I guess rendering them using Google's pushpins maybe wasn't the best approach. Perhaps something like this might be a little bit more useful. This is a heat map. It shows the density of data based on colors. And now we've got a visualization that we can actually use. So as you can see, there are clear hotspots of activity around downtown Seattle, near the University of Washington, a few more on the east side. There are several ways to do heat maps. If you want to do real-time heat maps with real-time data, you can use a JavaScript solution. This particular one uses thermo.js, which is a library that I kind of threw together last week. It's on GitHub. There's also a couple more well-established JavaScript libraries, heatmap.js, heatcanvas.js. I'll have links to those. Heat maps are another reason to pay really close attention to your coordinate system, however. Depending on which heat map library you use, or especially if you end up rolling your own, you may need to work in image pixel coordinates. A heat map is an image. It's an image overlay over the map. So as you're creating that, you're creating an image, you need to work in XY coordinates. And so you might have to convert between lats and longs and image coordinates. And when you do that, you need to make sure that you use the right math for a Mercator projection. Or better yet, you just let your tools handle that for you. Google Maps provides an API to do that. RGU does the same on the Ruby side. Here's a really quick view of the JavaScript for constructing a heat map using thermo.js. It's really simple. You take your Google map, you create an overlay object, throw a bunch of data points at it. It'll render it using a heat map image. Now, if you have lots of data, JavaScript might be a little bit too slow to render things in real time. This data was about 50,000 data points. It already took about 5 or 6 seconds of client-side time on a pretty fast laptop to render this on the client side. Now, if you have millions of data points, clearly this becomes unworkable. So generally then what you want to do is you want to pre-render heat map images or any kind of this kind of visualization into images on your back end. What you do is you create raster tiles, and then you store those image tiles in a database, and then you just serve those up as images. This is basically the way that Google Maps itself works. They pre-rendered all those map images into tiles, and then they serve them up. That's a little bit more involved process. We'll have to table that for a different talk because we want to go on to some additional things. So just to recap what we've done in this first project, we created a model to hold location data. Again, we used Google Maps' native coordinate system to store that data, and we had reasons for that. We loaded a bunch of data into it from Perks activity logs. We queried that data using a rectangular query. We saw how we do that in SQL, and we saw how to do that using the squeal gem. We then visualized that data using a heat map. So for our second project, what we're going to do is we're going to look up time zones based on location. Now, conceptually, this is pretty straightforward. Time zones are basically regions of the world, each one associated with a time policy. Now, there's actually an open database of time zones, world time zones. It's called the Olson TZ database, sometimes called the Zone Info database. It's pretty much universally used as a catalog of world time zones. Rails integrates with it right now. You probably have a copy of it on your own laptop's operating system. There are actually polygons available for this database. You can download them online. So if we download those polygons and create our own database using PostGIS, throw those polygons into our database, then given the location, given the latitude and longitude, we can query our database for which polygon contains that location, and that'll give us the time zone. So conceptually really simple. Now let's dive into the details, because this gets interesting. First, let's generate our model. Now, in our last example, we used the point type because we're storing point data. In this one, we'll use the polygon data type. Again, these are data types that are provided by PostGIS. Now, we also note that it might take multiple polygons to fully represent one time zone's area. For example, consider a coastline with a bunch of islands offshore. The Pacific time zone here in the US is like this. There are a bunch of islands off the coast of Washington State, a bunch more off the coast of Southern California. Each of those islands could be a separate disjoint polygon in this polygon data set, but they're all part of Pacific time. So we'll set up our model that way. We'll set up time zones and time zone polygons as separate tables and set up a has-many relationship between them. Now, we'll perform more or less the same modifications to the migration that we did before. Once again, we're actually going to use the Mercator projection for our spatial data in our database. In the last project, we did that because of the kinds of queries we want to run. In this case, we're actually going to do it because it's going to help a little bit with the geometric analysis that we're going to do. Once again, we'll create indexes, including a spatial index on the polygon column, and then we can rake db migrate. As before, we'll set up an RGO factory for the active record class, a little bit of ceremony that we have to do here. And then we need to obtain the data. Now, you can download time zone polygons from this website. It provides data in a shapefile format. This website there will be a link to this in the links page at the end. Shapefile, the file format that it's provided in, it's a standard format. It was created by Esri, which is kind of one of the old venerable firms in GIS. Shapefile is pretty much now the standard, it's a de facto standard format that pretty much every download of geodata that you're going to find is going to use that format. That includes census information, government downloads, you name it. Pretty much everything uses shapefiles now. Unfortunately, shapefile is a little bit of a crufty binary format, and so you need to parse it. For Ruby, there's a gem called RGO shapefile that does kind of the heavy lifting for you. Basically, it lets you do this. It lets you open the file, and then it gives you a stream of records. Each record in a shapefile comprises a geometric object, such as a polygon, and then a set of attributes. For our application, basically, we just want to take that information and then populate our time zone database. So here's the code for that. In this particular shapefile, one of the attributes in those records is going to be the time zone name. So we'll take that time zone name, and then we'll look up or create the time zone object from active record. And then we'll create polygons for that time zone. Now, a couple things to note here. First of all, this particular shapefile of the time zone information happens to use latitudes and longitudes as its coordinate system. Not all shapefiles use latitudes and longitudes. Some of them will use a projection, like a state plane projection or a UTM or some other coordinate system. This one happens to use lats and longs, but whatever coordinate system that the input data actually comes in as, we're going to transform that into a Mercator projection before we store that into our database. Secondly, remember that there might be multiple polygons in a particular time zone's record. So we do need to iterate over those and add the individual polygons to the database. So otherwise, pretty straightforward. We just load in the file and throw polygons in our database. Now, we'll circle back in a bit and take a look at some optimizations that we can do here. But first of all, let's take a look at how we can query. Now, remember the goal of our project. Given the location, we want to find the time zone that contains that point. And then, we want to find the polygon that contains that point, and then we can follow that polygon back to the time zone. So let's write a query method on our model that looks for polygons that contain the point. Now, our query here centers on the stcontains SQL function that I have highlighted here. I don't know if you can, yeah, I think you can see it pretty well. stcontains is a function built into spatial databases by PostGIS. It's available in your spatial database. And it's an SQL function. Most spatial queries that you're going to write are going to involve function calls. And here's where the Squeal gem really begins to shine. Squeal lets you write SQL functions such as stcontains here in a Ruby syntax, simply as if you were writing Ruby function calls. And Squeal takes that and then treats it as a DSL and then uses ARL to convert it to SQL for you. So effectively, you can write your SQL in Ruby. Active record by itself generally doesn't support SQL function calls very well. but using Squeal, you just write it in Ruby, and it does all the heavy lifting for you, doing all the coding and everything. This is awesome. This should be in Rails 4, seriously. Anyone from Rails core here, you ought to check this out. Squeal, it'll blow your mind away. Anyway, it's really easy to wrap this up now in a controller to provide a web API interface. And now we have a working time zone service. Okay, now let's make things a little bit more interesting. Seattle is largely surrounded by water. We have Puget Sound to the west of us and Lake Washington to the east of us. Now, if we look at the polygons in the database near Seattle, we see that the polygons that we downloaded, they only cover the land masses. They actually don't cover the oceans. They don't cover other large bodies of water. So what happens if I'm on a ferry out here in the middle of Puget Sound? A query for my location here is not going to land on any one of those polygons. So then what do I do? In fact, am I even in a time zone when I'm out there in the middle of Puget Sound? Well, by international convention, if a ship is in the country's territorial waters, then it uses that country's time zone. Now, what is meant by territorial waters? Well, there are actually a lot of different rules. There's exceptions, there's various international treaties and what have you going on. But in general, in many cases, territorial waters are defined to extend 12 nautical miles out from the shore. So in general, if I'm not directly inside one of the time zone polygons, but I'm within 12 nautical miles of one, then I should use that time zone. So in the case of this ferry, I'm still in Pacific time because I'm within 12 miles of the Seattle shore. So let's modify our query to handle this case. Now, remember this was our original query. It simply looks for a polygon that contains the query point. Now, if I'm out in the middle of Puget Sound, this query is going to return back nil. There's not going to be a polygon there. So let's handle that case and do a secondary query. And we'll look for any nearby polygons that are within 12 nautical miles of me. Now, this is a little bit more complex, so let's break it down into some details. This is our basic test here. This is our where clause. What we're going to do is we're going to calculate the distance between the point and the polygon in the database, and we'll make sure that that distance is less than a certain value. So here we use the stDistance function. It's another SQL function provided by our spatial database. We can write this whole expression, the SQL function call, the less than operator, everything in a Ruby syntax, and then Squeal will take that and convert it into SQL for us. Now, another thing to note here is that just like location data, distances are also relative to a particular coordinate system. Since our database uses a Mercator projection, we need to convert that distance, 12 nautical miles, to the corresponding value in Mercator space. And so here, this is the formula that performs that conversion. You can look up all this math on Wikipedia or something. It's one of the few things they actually get right over there. Now, what if there's more than one polygon within 12 miles of the query point? And this happens, if you remember that map, out in the middle of Puget Sound, there are a lot of islands surrounding that point. It might make sense just to look at all those polygons and take the closest one. So here what we've done is we've ordered those results by distance, and we just take the first one. And again, Squeal helps us here because its DSL works in the order clause just like the where clause. Active record by itself, the last time I checked actually, it doesn't even do string interpolation in the order clause. I'm not sure why, but Squeal gets around all of that and lets you use its own DSL there. So now we've got our full query. But hold on, we're actually not done yet. So Rails 3.2 has this nifty explain feature, and explain comes back and tells us that this query is really slow. Now, we do a little bit of digging, and we discover that PostGIS is not optimizing our stDistance queries very well. They're not using the spatial index that we created. And so what happens is the database ends up doing a full table scan and calculating the distance to every single polygon in our database. So it turns out that we can actually write this query a little bit differently so that the query optimizer can make it performant. And here's how we do that. Remember, we want to find the polygons that are within 12 nautical miles of a particular location. This is the same as drawing a circle of radius 12 nautical miles around your location, and then querying for the polygons that intersect that circle. So it turns out that PostGIS doesn't optimize distance queries well, but it does optimize intersection queries well. So we can rewrite this query. Instead of filtering on ST distance, what we'll do is we'll create a circle around the point, radius 12 nautical miles, and then we'll filter on intersections. So let's modify our code. Here, the ST buffer SQL function basically just creates that circle. In general, what it does is it takes a geometric object, which could be a point, it could be a polygon, or any other geometric object, and creates a buffer of a certain width around that object. So for a point, that's just a circle of that particular radius. Actually, technically, it's a polygon approximation of a circle, but for our purposes, that's close enough. So we create that circle, and then we test for intersection. And the query optimizer is happy, and we get fast results. Now, we have a few more minutes here, so let's take a look at one more optimization. Spatial data tends to be very big. Now, usually, big data means a lot of database rows. You might have thousands, millions, or more users, events, posts, or whatever in your system. And so when you need to search for something out of millions of rows, you make it perform it generally by using an index. An index eliminates most of those rows quickly so that you only have to search a few to find what you're looking for. Spatial indexes work the same way. They eliminate most of the geometric objects in the database quickly so that you only have to search a few, and so they're good for speeding up searches in tall tables with lots and lots of rows. But spatial databases or spatial data often has another problem. The individual rows themselves might also be big. In the polygon database that we just created for time zones, for example, many of those polygons have boundaries that follow coastlines, rivers, or other natural features. And so those boundaries are not straight. They're crinkly, and they have a lot of sides, sometimes thousands or tens of thousands of sides, each polygon. So generally, since we're storing a polygon per row, if you've got a polygon with 10,000, 50,000 sides in a row, now we ask the database, I want to compute the intersection, say, between our buffer circle and that polygon. That one test might be really slow. And the database index generally is not going to help us here. And so one common optimization technique when you're dealing with big spatial data is that you make rows skinnier by adding more rows. Specifically, we take these large complex polygons and we break them up into a number of smaller polygons, and then we just put those in new rows in the database. And so now the bigness of the data is only in the number of rows in the database rather than the size of each row. And now the database index can help us quite a bit more. Now, how do we break up large polygons? Well, one simple but really effective technique is to use 4-to-1 subdivision. This idea is pretty straightforward, has a fancy name, but it's simple. Basically, you just take a large polygon with lots of sides, you cut it into 4 quadrants. So you end up with 4 smaller polygons, each with about a quarter of the sides of the original. Actually, it's about a quarter plus 2, these 2 straight sides. But generally, you have a quarter of the size of the original polygon. And then if those smaller polygons are still too large, then you just recursively repeat until all the polygons are the size that you want. Now you can take all those smaller polygons, store them in separate rows in the database, and now your database index can help you sort through all of that. Now the question here is, how far should we recurse? How small is small enough for those polygons? Now that depends on a lot of things. Basically, what you have to do is you have to test and you have to measure. This particular graph here is a measurement from a project that I did a couple of months ago. It actually wasn't time zones, it was a different project, but a similar project where I wanted to take a bunch of large polygons and subdivide them, and I had to decide how far down to recurse. And so I tried different target polygon sides across the x-axis here. I benchmarked a bunch of queries on the resulting database. Now, when I had larger polygons on the right side of the graph, obviously the queries take longer. But when I subdivided too much on the left side of the graph, I ended up with so many polygons, so many rows in the database that the query time began increasing again. So somewhere in the middle is the sweet spot. kind of a target number of sides that will give you the best query performance. Now that sweet spot is going to be different depending on what your data looks like and what your application actually does. So make sure you do your own measurement here. This is the result here of that polygon subdivision algorithm on the Pacific time zone. So notice that where the shape is relatively simple with straight sides, such as around Nevada, the polygon does not need to be subdivided very much. But in a few places, such as the northwest corner of Washington, where Seattle is, you have a lot of coastline, a lot of crinkly edges, and so the edges become very complex and have a lot of sides. So the polygon there is subdivided more to keep the number of sides per polygon low. Sound complicated to implement? Well, not really. This was our original code here for reading the shapefile and populating the time zone database. We're just going to add the segmentation to this process here. Now, when we read polygon from the shapefile, instead of throwing it directly into the database, what we're going to do is we're going to run our 4-to-1 subdivision on it first until those polygons are small enough, and then throw those in the database. So this is what it looks like here with the entire segmentation algorithm. There's a lot of code here. I just want to point out a few key points. This method down here is the main workhorse of the algorithm. If we zoom in here, we'll see how to handle a polygon. First, we count the number of sides. Now, if there aren't that many sides, then we just add the polygon to the database as it is. But if the polygon has a lot of sides, then we subdivide. Now, first, we just create a bounding box around that polygon, and then we divide that bounding box into 4 quadrants. And we take the intersection between each quadrant and the original polygon, and we get the part of that polygon that falls within that quadrant. So now we have 4 smaller polygons, and then we just recurse. So as you can see, pretty much the entire algorithm requires just a few lines of Ruby. Most of that is made possible by the RGeoGem. It provides a number of really useful geometric utility methods for doing things like creating bounding boxes, subdividing them, calculating polygon intersections, and so forth. And that's it. So just to a quick recap of what we did in this project. We created time zone and polygon models as separate models. We have a has-many relationship between them. We loaded data from a shapefile that we downloaded online. We then wrote queries, 2 queries. The first one was to find the polygon that contains a particular point. The second one, we drew a circle around a point and looked for any polygons that intersected that circle, and that gave us polygons that are nearby within 12 nautical miles. Finally, we further optimized those queries by subdividing the polygons, trading width of the database for height so that the database index will help us. So we've gone through this really fast, but we're running out of time. So just so that you can get an overview of how these techniques are implemented, we've kind of just given you this basic overview. Now, if you really want to dig deeper into understanding this code, all these slides, along with plenty more reading material, will be online here. You can write down this URL. It's not live yet. We decided that in the interest of not having 100 people trying to download 20 megs of slides at the same time on our Wi-Fi, we'll delay actually posting this a little bit. So sometime a little bit later today, I'm going to actually post this page. So by the end of the day, you'll be able to download this. The slides will be online, links to all the software that we use, a bunch of articles, and various stuff that I've kind of curated, just a bunch of resources that will help you get started with your own geospatial projects. Finally, if you're interested in talking more about geospatial stuff, or if you'd like to meet other people doing interesting things with location, we're putting together a BOF, the 2nd annual GeoRails Summit, right here at RailsConf. Check the boards outside. I'm not sure how the schedule is supposed to be put together, but just keep an eye on the boards outside. Hope to see many of you there. Otherwise, thank you all for coming.